Okay, guys. So, what have we seen until now in the previous lessons? We've seen the core concepts of Solidity. We've seen variables. We've seen data structures, how getters and setters work with the view axis. We've seen how to perform transactions, best practices on clean code. And in this lesson, what we're going to look at the fundamental security measures in writing secure Solidity code with two key examples. We'll be looking at the token standards that have made what I think is the future of the finance world with Web3. And we'll also be looking at a introduction with oracles. So without further ado, this is the Solidity Masterclass Lesson 3. I'm Piero, and yeah, let's get into this. So before we go in detail about access control, which is the first security mechanism I want to talk about, I want us to imagine a scenario together, a scenario where we're building, let's say, the next big decentralized application. It's, for example, here with AI, I quickly depicted this scenario. It's like the next big ecosystem whereby we're rewarding users for their sustainable actions. I know it sounds familiar. It exists. It's called the Be Better DAO. But what's happening is that new users are being onboarded, everything is going great. But at one point, we have some malicious guy that is able basically to withdraw funds, is able to access the funds of the apps within the ecosystem without their permission, basically. Some access that's only restricted to the app admins, let's say. The result of this, the application's treasuries are drained, users are furious, and of course the project is in shambles. And after an attack like that, it's hard to gain back your reputation. This sounds scary, no? It's something that actually happens very often in the Web3 decentralized world. One infamous attack that happened 7 years ago was the parity multisig attack. In fact, the hacker was able, post-initialization of the multisig wallet, was able to add himself as one of the owners and therefore be able to drain one of these multisig wallets that at the time had $30 million in Ether, which today is around $600 million. So all of this just to introduce what access control is. So access control is one of the key security mechanisms in Solidity that allows to gate access to specific functions and operations within your Solidity smart contracts. There are two typical access control mechanisms, a role-based access control mechanism and a ownable-based, or known as ownable contracts. Role-based consists of a series of roles. So you're basically associating roles that allows you more granular control over your smart contract to specific users. In fact, let me quickly dive into an example of role-based access control so we can see this in action. Now, this is the repository I have locally. I will be sharing it with all of you. I'll actually be merging it with the repository we already have shared with the previous lessons. And in this repository, you will find all the Solidity contracts we'll be looking in this lesson. So the first thing is the role-based access control example. We can see here an enum. So enums in Solidity are actually disguised as uint8s because Solidity operates at a 256-bit word basis. And the smallest primitive type is a uint8. In fact, cool curiosity is that Booleans that can be stored with 1 bit, in reality in Solidity are actually 8 bits. Just a curiosity on that. So in this case, what we have is an enum with 2 roles, an admin and a user role. But we notice also a, let's call it none role, but in reality, it's not a role. It's simply the first value of the enum. This is because, as we've seen in the previous lessons, upon declaration, Solidity also has a 0 value. So if we look at the mapping here where we are associating an address to a role, what happens is that for every address, what is actually initialized is the first value of the enum because we're associating an address to a role, which is this enum here. So if I did not have this none role here, basically, what would the 0 value be? It would be an admin. And this would be a really faulty implementation, meaning that every user would be an admin from the start. Instead, with the none role, we're actually assigning no role to all the users. But then if we look at the constructor, so this is called upon deployment of the contract, what we're actually assigning to the deployer that is accessible through the message.sender global Solidity variable is the admin role. This is all just to quickly give an overview of how the access control works, which we'll see shortly. So the current state upon deployment is that the deployer has the admin role. Here, basically, his address is associated with the admin role, and all other users have the none role. In fact, let me quickly copy this contract and head over to Remix. Remove these. I was doing some deployments before. We go to the role-based access control contract, and yeah, there it is. It's the same contract we've seen in VS Code. What is Remix? Remix, if you haven't seen it before, is basically a web-based IDE for building, compiling, and also deploying smart contracts. It has a lot more features. I know it's evolved in time. You can even do testing, etc. But for our purpose, it will simply allow us to see the contract, compile the contract, and interact with it. And in this case, what's happening is that with Remix, I can head over to the Solidity compiler tab, select the Solidity version, because here we've defined with Pragma which Solidity versions are compatible. So 0.8.22 is perfect. Let's go ahead and compile this. And then in the next tab, the deploy and run transactions, we can actually deploy this contract. But where is it being deployed? It's being deployed in this environment here, the Remix VM Cancun fork. So it's just a local environment within Remix. But you can even deploy into actual blockchain testnets, mainnets, by specifying maybe through MetaMask. So injecting through MetaMask, it triggers your MetaMask account. You can perform transactions with that, or even Wallet Connect. Unfortunately, because VeChain is not JSON RPC compatible out of the box, I know we have plans on extending this at our API level. But for now, if you want to use Remix with VeChain, you would need like a proxy, an intermediary that receives JSON RPC compatible requests and then forwards them to our nodes in a past and compatible way for our nodes. I know the SDK team has built a proxy around that, so if you want to use the Remix environment, you can do that. But back to us. So role-based access control contract, in this case, we can see why I'm using Remix. It simply allows us to visualize what the publicly accessible methods or functions are of this contract. In this case, we have the admin function, an assign role function, a user function, and a roles function. Quick curiosity here is that the roles function cannot be found in the function. But in reality, what happens is that each publicly declared state storage variable is actually also a getter. So you can even read that those values, in this case, the associations of the mapping, as if it was a getter function in the smart contract. So just a quick tip there. So let's see if our deployer, which is this account here, has the admin role, as we said, during the constructor or the deployment. In fact, let me quickly paste this address here, call the roles, and we can see the result is a uint8, because enums are behind the scenes uint8s, and the value is 1. Because we can see here that none is the 0 value of the enum, 1 is the admin value, and 2 is the user value. And this is exactly what happened during the construction. We assigned the deployer to the admin role. And here comes the cool part of this access control mechanism. We have modifiers that allows us to gate access to specific functions. So in this case, where the gating happens is within these functions, in particular before the execution of their bodies. In fact, a modifier is a particular construct in Solidity that allows to execute blocks of code before, after, or even before and after the function's body itself. So in simple terms, what we're doing here by specifying only admin as the modifier of this assign role function is that we are requiring, before the execution of the function's body, that the caller of the function has the admin role. Otherwise, we're reverting with a custom string error that is access restricted to admins only. Same exact thing for the only user. It restricts for the user role. So let's check, for example, if our deployer that has the admin role can perform these only admin operations. For example, let's go ahead and call the admin function, and we can see it correctly executes. It successfully executes. But if we try and call the user function, we should expect it to fail because the deployer does not have the user role. Let's go ahead and do that. And there you go. We see the transaction reverts. And the reason provided by the contract is that the access is restricted to users only. So we can see the only user modifier is successfully performing the role-based access control. But let's now try and assign a user role to a user, basically, and we can perform the user function. So let's go ahead and select the second account, let's say, copy this here. And then we go to the assign role, we paste his address, and we specify as the role to assign the second, the number 2, the integer 2, which actually is the third value of the enum because it's 0 indexed. Let's go ahead and assign the role. Yeah, this reverts because I'm with the second account that does not have the admin role. So let's go back to the admin account and perform this again. And now it works. Why did it revert? Because basically, when you perform a transaction with an account, he becomes the caller. So you need to select the actual account that's performing the transaction. And that is checked again with the Solidity global variable, which is the message.sender. Let's check if the second account has the user role we just assigned. So let's copy his address, go back to roles, call it, and we can see that the result is 2, because 2 is the user role in the enum. So what I expect now basically is to be able to perform the user function. And there you go, it's successful. But if I try to perform an admin function, which is obviously restricted to admins only, it should revert. Great, so this is a simple example of role-based access control mechanism, but what I highly suggest is to not build this from scratch, especially if they are battle-tested, if there are battle-tested solutions, standards, open source solutions that have been validated through time in the community, in the Solidity developer community. Out of these battle-tested solutions, we have OpenZeppelin. We already saw a quick introduction with the previous lessons to OpenZeppelin, but in this lesson, we'll really focus with the standards implemented by OpenZeppelin, such as the access control mechanism. So let's head back to our repository and look at the access control mechanism by OpenZeppelin. So how this works, if you want to implement access control in your smart contract with this library, is you need to simply extend with the access control abstract contract by OpenZeppelin. You can see this contract here is imported in our contract, and all you have to do to utilize this contract is install the library, which is OpenZeppelin/contracts. We'll see in the next lesson with the upgradable contracts, which is quite different, and OpenZeppelin offers a different set of smart contracts for upgradability that you can perform the same concepts, but with an upgradable form to it. Upgradability is there, and we'll see more in detail in the next lesson, because by default, once you deploy a contract, it's immutable. So you need to create a way through various different patterns to be able to maybe update the logic or utilize a proxy and then point to a new logic contract. So in general, allowing upgradability on contracts that by default are immutable once they're deployed. But back to us, what is the access control mechanism by OpenZeppelin? Like, how does it differ with our solution? It differs primarily with the way we get roles and how roles are specified. So in our case, we had an enum. Enum has its limitations. As we saw, it's not really clear to understand what the value is within the enum. It's limited by its primitive type or to 256 values. It can be extended over 256, but by default, it's a uint8. And also, it's not too flexible, our solution. Instead, with this solution, what happens is that roles are defined by bytes 32s. So it's simply the hash using kekak of the role that has usually this syntax, which is a string. So you have the role name underscore the role, and the hash results in a constant of a bytes 32 primitive type. This means that constants are directly inside the bytecode upon compilation of our smart contract. It makes it a lot more gas efficient. And at the same time, it occupies an entire Solidity storage slot, because we know that Solidity operates on a 256-bit word basis, making it very efficient to compare roles that occupy an entire slot. You don't have to perform additional processing. There's no more memory overhead in checking if a role maybe that has a smaller primitive type is equal to another role by doing casting, conversions, etc. So it's very efficient. And the second key thing of this extension of the access control mechanism is that it offers great flexibility on granting, revoking roles, and checking for specific roles. The last thing that is quite different also with this implementation is that there is a default admin role. Imagine the default admin role like a super user, a super admin. He actually has access to all the other roles and can grant and revoke all the other roles too. While, for example, an admin role in this case can't manage a minter role and vice versa. And to check through the gated access like we saw before, all you have to do is utilize the only role modifier, which is specified again in the access control implementation. And this only role modifier simply checks if the caller of that function that then is preceded by this modifier actually has the specified role. So in simple terms, when we call, for example, mint token, we're checking if the caller has the minter role. Add minter, if the caller has the admin role, etc. But I want to also show a quick edge case that you need to be very careful on utilizing access control of OpenZeppelin regarding the default admin role. So let's head back to Remix. Let's go to the OpenZeppelin access control. Again, let's compile and deploy. So here we can see the deployed contracts, my contract. Yeah, there you go. So first of all, you can see there are a lot more functions because these are all the publicly accessible functions that we are extending from the access control function. But the thing I want to show you here is this specific method here. So we have an add minter that can be performed only by an admin role. But then what's happening is that we're granting a minter role from that caller. And we said that this can't happen. Like if I only have an admin role, I can't manage a minter role. This can only be done if I have a default admin role. So if I call this add minter with the deployer, because we see the deployer upon construction received both the default admin role and the admin role, means that the deployer is able to call this. But if I instead call this only with an admin role that does not have the default admin role, we will see that it reverts. So let me quickly showcase this. So we have this account here. Okay, the second account is the deployer. Now, if we go and do add minter, say we add the, let me see. So say we add the third account, okay? Let's copy this address, go back to the second account, we go to add minter, and this works, okay? This works, again, because only role is passed because he has the admin role. And then grant role is passed because he has the default admin role that allows him to grant access to other roles too. But what happens if I call add minter with an admin role only? The modifier passes, so he does have the admin role, but he does not have the super admin role, the super user role to grant on behalf of other roles. In fact, let me quickly demonstrate this. For example, let's go back to our second account, which is the deployer. Let's go and grant the admin role to the, let's say, fourth account. Okay, let me copy this, go back to the deployer. So we're going to grant role. Let me paste quickly the address. So the first parameter we saw is the role. So the admin role, we can simply get it from here. We can see it's a byte 32. Copy this, go back to grant role. Okay, so we've granted the admin role to the fourth account. Let's go to the fourth account to verify this. Copy, let's see, has role. Again, let's paste, copy the admin role. And has role is true. Yeah. So the fourth account now has the admin role. Again, all of this to explain that having an admin role, so passing this modifier, does not guarantee that then you can perform the grant role within the adminter functions body. In fact, let's go ahead and add minter, for example, and we can see obviously that it fails. Let me expand this. It's failing with a custom error because you noticed in the OpenZeppelin standard, we're using custom errors which allow more flexibility around errors. It's not only a string, you can even add parameters. And it's reverting because access control is unauthorized by the account because the admin passes, okay, but it does not pass the grant role who is not allowed basically to grant a role on another role. Great, so this is how access control works. I hope it was not too complex. And last but not least, regarding access control, there is the ownable contract. This is a lot simpler, so a lot easier to understand. It's like owning a contract, basically. Usually, an owner is set up on deployment. And what happens is that you have a publicly accessible variable or even a private variable whereby you're setting who the owner of this contract is. And the simple modifier in this case is for only owner access control restricted functions, you utilize the only owner modifier. So only the owner can perform these operations. For instance, I don't know, withdrawing funds in a staking contract, even though that shouldn't be possible, it's just an example. And one other key element in ownable contracts is the fact that you can transfer the ownership. So you can transfer that ownership from one account to another. Great. So this was access control. Hopefully it didn't take too much time. Okay, 24 minutes, a bit long. Let's go to the next topic. Second key security measure we've learned through, unfortunately, hacks and exploits in time is the reentrancy attack mechanism, or better, the prevention of reentrancy attacks. A reentrancy attack is a particular attack that starts basically when an attacker is able to re-enter in a loop, basically, a function, and does this attack for an objective. For example, draining funds inside a smart contract. I don't know if you guys remember back in 2016, but another infamous attack happened, the so-called DAO attack. And at the time, an attacker through a reentrant attack was able to drain $60 million in Ether, which today I imagine is even over $1 billion. How this works is we have a vulnerable contract that does not implement the so-called checks and effect pattern, which we'll shortly see how this works. Therefore, the balances are not updated, and the attacker is able, through fallbacks and recursive interactions, withdraw funds before the smart contract actually specifies that the attacker doesn't have any more funds to withdraw. So he's able to withdraw more than the amount he deposited, let's say. Let's see, in fact, this in action. So let's go to the reentrancy vulnerable. And this simple contract is an example of how a smart contract can be vulnerable to reentrancy attack. So this is very simple. You have a deposit function. A user is able to deposit a certain amount of native currency, in this case, to the smart contract. And we have a withdraw all, which allows the user to withdraw all of his funds deposited from the smart contract. We have a simple check that the user has balance deposited. And then we have the basically non-reentrant attack implementation. The non-reentrant prevention attack implementation. So what happens here is that we are sending back, this is a way to send native currency in Solidity to the caller, the tokens he deposited. We are checking if the transfer was successful, and then we are resetting his balance. Now, what you can understand here, let me quickly draw on top of this. Let's imagine this scenario, basically. So let me get my pen. Okay. Let's imagine a depositor calls the withdraw function. Okay, checks pass, he's deposited, and then the tokens are transferred back to him. Now, imagine a case where the receiver is actually a smart contract. So the receiver is able, upon receiving the native currency, in this case, Ether or VET, is able to then call again the withdraw function before the balance is updated. What happens here is that we have a reentrant attack. So basically a loop where the caller is able to drain more than the amount he's deposited before the smart contract actually updates his balance. And this is exactly what happened in the 2016 DAO attack that drained so many billions of dollars. And to prevent this, we'll see it's simply the checks and effects pattern or specifying state before interacting with the external contracts. In this repository, you'll also find a test for each of these contracts. So you can take your time, look at how the contracts work more in detail, look at all their edge cases. And here, let's go to the reentrancy vulnerable test. Look at this test here, which depicts exactly how the attack happens. So once we deploy the deposit account, we deploy the attacker smart contract, and we simulate that a normal user deposits 10 Ether. What happens here is that the attacker now can perform his attack. how the attack happens is through calling an attack in his smart contract. So let's go to the attacker contract. How this works is very simple. So the attack function simply deposits in the vulnerable contract an amount of ether we specify. In the test, we specified basically 1 ETH. And after depositing, what the attacker does is he initiates the attack. So he calls the withdrawal function. So the attack itself does not drain the vulnerable contract, but how it's drained is through the recursive reentrant attack that is with the receive function. Receive is a particular function in Solidity that allows a smart contract to define operations to be done upon receiving native currency. So in this case, once the vulnerable contract sends the native currency back to the attacker smart contract, this function is basically triggered. And what it does, it checks if the vulnerable contract still has balance to drain, and it recursively, you see, calls withdraw. So every time that loop happens until the contract is drained, and we can see, in fact, in this test here, after the attack is done, the attacker can then withdraw from his attacker smart contract, and there are some checks to check, obviously, if he drained the contract. So let's quickly do this. So we deposited 10 ether, and we expect, therefore, the attacker to have 10 ether. And we can see, in fact, the drain amount is 9.999, etc. So this is 10 minus the gas fees, basically, that he incurred for performing this attack. How do we prevent this? We prevent this with the checks and effect pattern. So the checks and effects interaction pattern consists of updating state, involved state of the transaction before external calls. In this case, before transferring the native currency back to the attacker's smart contract. This means that if the attacker tries to recursively attack and withdraw, because the balance is already updated before we interact with the contract, what happens is once he receives the native currency and withdraws again, this is already reset, the check fails, so he's not able to reentrantly basically attack the depositor smart contract. Again, this is a solution that requires obviously knowledge of this pattern, but OpenZeppelin even offers the non-reentrant modifier, which checks that a function was not called previously. It simply looks for a status. If a function is called, its body has been executed, then the status is set as entered. So if a reentrant attack happens for some reason before the termination of the smart contract's body, then it would revert because the status has not been reset. In fact, what you can see here is a typical example of a modifier where operations are performed before and after the execution of a function. So before, we're checking if the function is not entered, and after, we are resetting the function. So if the reentrant attack happens before the reset of the status, it will fail because we have not terminated the execution of the function. So you have two ways. Or you utilize the checks and effects pattern, and you must be very careful, or you simply put the non-reentrant modifier, even though it might consume a bit more gas, but you're certain that reentrancy attack can't happen. Great, so this was the reentrancy attack explained, and these were the two key security measures I wanted to talk about, which are very common in Solidity exploits, together with other kind of attacks, but they're more around the token standards. In fact, talking about token standards, let's look at what they are. So again, let's think before we go into detail of another story here. One of the stories we saw before. In this case, we are inside a mall, for example. Inside a mall, we know that customers are able to buy goods with a currency. They're able to purchase maybe unique items, rare items, limited edition items. And they're even able to grab, let's say, combo deals. For example, I go to my favorite tech store, I buy a new laptop, and it comes together with some batteries, let's say 10 batteries for some reason. We're in the imagination sphere right now. This is all to basically give an analogy of how Ethereum works, and in general EVM-compatible blockchains like VeChain work. Imagine this mall at a global scale. So All of this, like all these interactions within the ball, are able to happen thanks to a set of rules, thanks to a set of standards that each store adhere to, follow, in order to make the experience as smooth and as seamless as possible. Same exact thing needs to happen in a open source decentralized environment like blockchain. Without standards, you would have complete confusion. You wouldn't have the possibility for wallets, tokens, smart contracts to be able to communicate within each other and minimize as much as possible exploits and attacks. In fact, the first, let's say, token standard, ERC token standard that has made possible, I believe, even why we're all here, is the ERC20 standard. We can imagine the ERC20 standard as like the mold's currency. In fact, in this representation here, we have this person that's buying some goods with the Better token. In fact, the Better is nothing else than an ERC20 token. And how ERC20 tokens work is ERC20 in particular defines the standard for the so-called fungible tokens. A fungible token can be seen basically as a equivalent measure. So you can compare each fungible token to another. It's like they're interchangeable between each other. There's no difference. In simpler terms, imagine like vet, like one vet is equal to another. You can interchange them. There's no way to say that my one vet is completely different to your one vet. They're exactly the same. This differs from the ERC 721 standard, or the so-called NFTs that we'll see later. Why? Because you can't, at a technical level, say that each NFT is equivalent to another. But how does the standard work exactly? I want to show you the interface quickly. So let's, for example, go to my token. And this is the ERC20 standard. So when you see a token that is an ERC20 token, you can expect that it implements the following methods. The following methods are the total supply, so you can know what amount of tokens are in circulation. You can know the balance of a specific account. You're able to perform transactions such as transfers from, and approvals that we now see a bit more in detail exactly what happens and how approvals work. And you have like getters like allowance. You can know the allowance of a specific spender of an owner, but we'll see that more in detail soon. Then you have commonly two events. You have a transfer and an approval event. The transfer event is actually quite flexible. We'll see why, based on the values that are passed to log the transfer that happens. And we have the approval also that specifies an amount we approve on behalf of an owner for a specific spender. Here, there's a sample implementation of a token, but this is just for demonstration purpose. I'd like to go directly into the OpenZeppelin implementation of ERC20. So here I've simply cloned the OpenZeppelin contracts repository, the one we imported for the access control mechanism. And we can see that the ERC20 contract is here, and this is how it's implemented. So you have a series of storage state variables. Of these, we have the balances, which is a simple association of an account to the balance he owns. Allowances is a double mapping. So we're associating an owner to a spender to the amount of tokens. Well, not really tokens, but we'll see, let's call it value, to a value that we are allowing the spender to spend, transfer, manage on behalf of the owner. Then we have the total supply, which stores how many of this ERC token are in circulation. And then we have simply the name and symbol. These are maybe the most seen at a UI point of view because they allow you to show exactly what token you're talking about. For example, our favorite tokens, we have a name, and we can have also a symbol, which is typically like the stock ticker, let's say. For Better and Vote, the tokens of the vBetter DAO, they have the same name and symbol, just a quick fact. Upon construction or deployment of the ERC20, we're simply specifying the name and symbol. What is the decimals? Decimals is an interesting topic of ERC20 tokens. Decimals represent basically how many units form one token. In simpler terms, imagine decimals like the cents to the dollar. You can represent $1 as 100 cents. In this case, we're saying that one token has 10 to the 18th way. Way is the standard, let's say, identifier for tokens with 18 decimals. And Wei, I also added here, its name comes from Wei Dai, a famous Chinese cryptographer that created a publication in 1998, if I'm not mistaken, called B-Money. He was one of the predecessors of digital money white papers. In fact, Satoshi mentioned his study in the Bitcoin white paper. So just a curious fact on why it's called Wei. Now moving on to the core functions of ERC20, we have transfer. So transfer is, as the name suggests, allows us to transfer a specific value, a specific amount from the owner to a destination address specified by the to address. I say owner because transfer is callable only by the owner. In fact, here we check who the owner is. Inside transfer, what happens is we do a couple of checks before calling the core function, internal function of the contract, which is the update function. These checks are the from and to address are different from the zero address. Remember I said that the transfer event is quite flexible. This means that you can basically utilize the same event to indicate special types of transfers. These special transfers are mints and burns. In fact, when you mint a token, you're actually inflating the supply. And you're specifying as the from address of the transfer, the zero address. In fact, the zero address is a common identifier in Solidity to specify these kind of special events, these kind of special functionalities. Whilst the to address, if it's the zero address, in this case, we're burning the token. We're sending the token to the zero address, which no one has access to, obviously. And in this case, we're utilizing the to parameter of the transfer event as the zero address. So in case of transfers, what we're doing is checking that it's not a mint and a burn, and then proceeding to the update function. What update does is a generalized form of doing basically transfers and checking if we're doing mints and burns all together. In fact, if the from address is the zero address, what we're doing is minting, so we're inflating the supply. Then if it's not the zero address, meaning it's a EOA or a smart account, a smart contract, we're checking if the balance of the from address actually is enough compared to the value we want to transfer. If not, we are reverting with this insufficient balance custom error. And if the value is less or equal to the from balance, we're doing an unchecked operation. Quick curiosity on unchecked operations, they're just like normal operations, but what happens is Solidity doesn't perform underflow or overflow checks. It's a way to save some gas because since a specific version of Solidity, overflows and underflows are checked natively, let's say, without, but that obviously means that we're increasing the gas cost because of these checks. But because in this case, we know that the value is less or equal to the from balance and less or equal to the total supply, this means that this substitution operation can never go below zero. So we can efficiently perform an unchecked operation here. Now, if the to address is the zero address, again, it's a burn. So we're deflating, we're removing the value from the supply because the tokens are being burnt. And if it's not, again, it's an EOA or a smart contract, we are adding, so we've removed from the origin address and we're adding it to the destination address. And again, here the transfer event is being emitted. And as I said before, we have these particular cases where if from or to are zero addresses, then we can, through indexers or on-chain subscriptions, understand if we're talking about mints, burns, or simple transfers between accounts. Last but not least, regarding the ERC20 standard is the approval. So let me quickly look for approve. There you go. So what is approve? Approve consists of a functionality in the standard that allows an owner to specify a spender to be able to basically manage, transfer, burn those tokens on behalf of the owner. Why is this allowed? This is allowed, for example, if we need a contract to basically perform some operations with our tokens for us. Simple example, the vote contract in the vBetter DAO. If we want to convert Better to vote, we need to approve the vote contract to be able to transfer Better for us to the contract, and then perform the conversion to vote and send back the vote to our origin contract. Simple example. And how it works is instead of transfer, in this case, we need to utilize transfer from, because transfer from allows spenders to transfer tokens on behalf of owners. And the allowance is simply checked by a pre-executed function, which is the spend allowance function. And this function, it should be down. Yeah, here you go. This function detracts the value we are transferring from the allowance if the allowance is less than the maximum value of the unsigned integer 256-bit value. What does this mean? This means that if I approve a contract or a spender in general with the maximum value possible in Solidity, actually what I want is infinite or unlimited access to my tokens. It's a way to not have to continuously allow once the allowance is below the amount the spender can transfer. Instead, if we specify a value less than the maximum uint 256, then the allowance is actually detracted each time. In fact, you can see this check happens exactly here. But I imagine your senses are tingling hearing these things because it's possible that a user can exploit this allowance feature. In fact, this is a great, I don't know if I want to call it vulnerability, but it happens so often that malicious contracts ask allowance for tokens of a user, and then that means that the allowance given means that the contracts can move the tokens of a user and basically drain your wallet. So you need to be very, very careful on when you're performing this allowance operation. And fortunately, wallets have improved a lot in time, giving you like a preview of what actually is happening. So if an approval is happening, a preview of that approval happens before the signed transaction. Sorry, my dad is calling me. I have to call back. Yeah. So I invite wallets in general to implement this. I know like our wallets have this in plan, but like other EVM wallets already do this because it's a great, let's say, functionality to prevent exploits of this case. So yeah, this was the ERC20 standard. Let's quickly move on a couple of extensions. What are extensions? They're simply add-ons on the standard that allow some common functionalities. For example, we have the ERC20 capped. Capped means that the total supply cannot exceed the cap. In fact, better is a smart contract that actually extends this ERC20 capped abstract contract. This means that once a cap is defined, after performing the update, we actually check if the new supply is greater than the max supply, and we revert. Flash mint is an extension, a curious extension here that allows minting tokens that need to be returned plus an eventual fee within the same transaction. How it works is that you have a receiver that implements an IERC 3156 flash borrower interface, and this interface simply defines how the on-flash loan, which is the callback the flash mint extension needs to call, how this callback basically returns a value. It's a way for the ERC20 flash mint contracts to understand that the receiver is actually compatible with this standard. In a quick overview, what happens is we're checking the max loan, we're checking if there's a fee defined, we're minting this amount of tokens, we're calling the flash loan on the receiver contract, he performs his operations, and then once his operations are finished, the ERC20 flash mint contract sends back the fee and burns the tokens basically that he minted for the receiver. This might sound complicated. Like, why would we do this? Imagine scenarios like arbitrage opportunities. You want to quickly borrow a token and send it back all within the same transaction. So you maybe do an arbitrage opportunity, you find a difference in price, you're able to borrow some tokens, do some DeFi operations, return those tokens in the same transactions, plus an eventual fee if the fee is defined. Why Flash? I don't know if I mentioned, but Flash is exactly because all these operations need to happen within the same transaction. This is a ERC20 flash mint, so it's a token that we're minting and burning the supply. But you will commonly see other use cases like liquidity providers, lending protocols. They don't really use this exact example, but they use liquidity pools that offer the similar functionality. So in that case, you are actually borrowing maybe an ERC20 token or a native currency, and you are giving back that ERC20 token or native currency within the same transaction plus a fee, again, for opportunities like arbitrage. Last extension I wanted to quickly go into is the ERC20 votes extension. This one is particularly at heart for us, for the vBetter DAO, because the vote contract actually extends this ERC20 implementation. What this implementation allows is checkpointing of the voting power of a user in time. But why would we need this? Imagine a DAO, a decentralized autonomous organization, a governance system in general, whereby the voting power is defined by a token. Now, if we did not know what the voting power of a user was in time, let's say a specific block or a specific timestamp, what could happen is, given us a proposal, a user could find it particularly beneficial for him and maybe utilize opportunities like buying that token to enhance his voting power, or maybe borrowing it during the proposal period, and therefore manipulating post-proposal what the outcome could be. This is just one scenario, but it's quite typical for governance systems. And the need, therefore, of checkpointing your voting power is fundamental in these kind of scenarios. How it works is you have the extension of the votes contract. Votes contract utilizes a particular data structure called checkpoints. Checkpoints, you can imagine it as key value pairs, whereby the keys are always sequential. So each key added, pushed, let's say, to the array or the checkpoints array is always greater than or equal to the previous value. What does this allow? This allows efficient data retrieval through binary search, making the operation of storing O of 1 and also retrieval O of log of n, where n is the number of possible checkpoints, let's say. And this means that we are adding a key functionality of checkpointing without making the gas costs increase too much for the scenario like we depicted. In the case of the votes contract, we are simply checkpointing the votes by doing the transfer voting units. So you can see every time we are doing a transfer, whether it's a mint, in this case, we're adding to the total supply. If it's a burn, we're decreasing from the total supply in a checkpointed way. Otherwise, if we're transferring these voting units, what we're doing is we're checkpointing the balance of the from and the destination address upon this internal method. So we're basically checkpointing at a specific time, by default, the block number, what the voting power was of the two involved addresses at that transaction. And what the getters here are used, for example, in the vBetter DAO, are the get past votes, which allows us to know what the voting power was at a specific time point, at a specific block. And you can also use get votes, which is a generic one, is a simplified one that simply returns what the current voting power is, so the latest checkpoint. Last but not least, we have also a delegation concept in the ERC20 votes. So you can even delegate your voting power to another account. This allows opportunities like community pooling. So you can pool your voting power together, maybe increase your voting power for certain scenarios, or you can just delegate it to yourself and be able to vote, obviously, on your behalf. By default, the vote contract in the vBetter DAO already delegates to yourself upon receiving your first vote tokens. Yeah, this was the ERC20 standard. I hope it was quite clear. We went through some extensions, and I want to quickly go to the next one. I know there might be questions, but unfortunately, there are still so many topics, and we have 40 minutes. So ERC721. ERC721 can be seen as the rare items in the mall. The rare items in the mall, in this case, I just depicted a statue, because like in my nearby mall, they recently added like these, I don't know if they're real or not, but these sculptures, and it gave me this idea that inside the mall, you know, you can find these unique rare items, and maybe, I don't know, a customer wants to even buy it. Why do I give this example? Because ERC721 tokens are the so-called non-fungible tokens. So they're the opposite of the ERC20 standard. They're opposite of the fungible tokens. What this means is that you cannot exchange on a one-to-one basis one token for another, because at the most atomic level, each token has its own identifier. It's not equivalent to another. Some real-world examples we've seen, for instance, in 2021, we had the famous profile picture NFT collections, whereby each token not only had its own token ID, but even had its own representation, that so-called metadata. For example, the Bored Ape Yacht Club, there were these monkeys, and each monkey had its own image. That's just a perfect example of how the ERC 721 standard makes all tokens different. But you can have obviously complex, not complex. You can have different examples to this. For example, the VBetter DAO, we have the Galaxy member system, and within the Galaxy member system, that's an ERC 721 collection, you can have tokens that have the same metadata, basically, because we know the Galaxy member system is a level-based system that gives you more voting rewards multiplier based on your level. And if you have a token of the same level of another user, that means that your token ID is different, yes, but the metadata associated to your token is not. In simple terms, let's look, for example, at the Galaxy member NFT system. We can see that, let me see if this is the right one. Yeah, we can see, for example, that all level 1 or Earth-based NFT systems of the Galaxy member system will have the same metadata. In this case, our new and lovely mascot, BMO, that is at Earth. Yeah, so back to us. Let's see now how this interface works. So Open Zeppelin, contracts, and ERC 721. Similar to ERC 20, we have these storage state variables that have same connotations as the ERC 20 plus some nuances, like some new instances. So name and symbol are the exact same. We have owners. In this case, we are associating a token ID to a specific account. So we're checking who the owner is of that token ID. Again, because each token is not the same as another, it has its own identifier. Then we have balances. This holds how many tokens of the ERC 721 standard an owner has, because you can own more than one if the smart contract allows it. Then we have token approvals and operator approvals. So token approvals is similar to the approval process in ERC 20, but in this case, we're approving a token ID to be transferred, managed by a specific address. Instead, operator approvals, we're approving all of my token IDs to be able to be managed by an operator. So this is the key difference. The part before looking at how the core update functionality works is the token URI. So this is the key difference, let's say, with ERC 20 compared to ERC 721. We have the existence of this metadata concept. What this means is that if the use case of the ERC 721 standard, like we said, profile picture or VBetter DAO Galaxy member system requires it, you can associate to each token ID some specific metadata. This metadata allows you to, for example, define what the name of the collection is, what a description is, some attributes. For example, we'll see soon like what the level of this NFT is, and also, if needed, an image. So what actually image or media in general that that token has, whether it's a static image, a dynamic, a GIF, a video, whatever, a text base. You can literally have infinite use cases. And how this works, let me go back to our inspector. Again, inspector, if no one has used it, is our way on VeChain to interact with contracts. It's similar to like the below section of the Etherscan forks. It allows you to interact directly with contracts. You specify the ABI and address. So in this case, what I've done is specify the address and ABI of the Galaxy member contract. If we head to the token URI, and I specify, for example, token ID 1, what it returns is this IPFS canonical form. Because usually what happens in a decentralized environment is you want the storage of your metadata to be as decentralized as possible. Some common solutions is using IPFS, the interplanetary file system, or maybe Arweave, which is similar, but in that case, you pay for the amount of storage you need. So let's see exactly what this metadata looks like. Let me copy this, go to our gateway that has also recently been released. So if you need a performant gateway, make sure to contact the gateway, the IPFS team. And you can see here the base URI, which holds basically all the possible metadata for all the tokens. In this case, it's only 3, not because there are 3 tokens, but because there are 3 levels So this is a custom implementation of the standard, but each of these basically specify the metadata for each level. So you can see here you have the Earth level, then here you have the Moon level, which is the level 2, and here you have the Mercury level, which is the level 3. And you can also specify like attributes. This is another standard, but more for like marketplaces, secondary markets to showcase the attributes of the NFT. In this case, we're specifying as the trade type, the level, and the value is 3. Like we said before, we have the image, and let's see what the image of this level is. And there you go. Again, BMO, in this case, he's on Mercury collecting some stones. Quickly, let's look also at some extensions. So ERC 721 extension, consecutive extension, this one allows for batch minting. Imagine scenarios where you have a fixed supply upon deployment. You have already a predefined supply of NFTs and predefined owners. You want to actually batch mint in a gas efficient way. You can use this standard, which allows upon deployment to batch mint all of these tokens. What happens is through the mint consecutive function, you're not actually associating for each address what the token ID is owned, but you're simply checkpointing through the checkpoints library we saw before, the start index and last index of the owned token IDs of a specific address. And because this is consecutive, you cannot have any lapping. Also, because this can basically cause problems if you do it after deployment, the restriction of this standard is basically only during deployment. So you can mint consecutively, and the key difference here is that you are actually emitting a specific event of the standard, which is the consecutive transfer. So you're specifying the next token ID, the last token ID, and the from address. So in this case, we're minting, so the 0 address and who the destination is. Key thing here are two particular data structures. We saw the sequential ownership, which is checkpoints, but also the sequential burn. In this case, it's a bitmap. I want to quickly look into bitmaps and how they work and why they're commonly used in Solidity for gas efficiency. Because if you notice here in the update function, when we're performing a burn, what we're actually doing is setting through the bitmap for that token ID, the fact that it's burned. So we're setting that bit to 1. How this works, let's quickly go inside bitmaps. We can see it's a mapping, buckets to UNT 256. But what you actually need to imagine here is that a bucket holds 256 bits within it. So imagine I have, I don't know, token 1200, and I want to burn that token. We saw that it's being set within the bitmap. We're doing basically sequential burn.set token ID. And we can see here what in reality happens is that we're getting the bucket, first of all. It's like performing modulo of 256. So we're doing 1200 modulo 256. You're getting the bucket within that token ID stored. And to know exactly which position within the 256 bits that token ID is performing this mask operation. So it simply masks within those 256 bits the position in which you want to set that value. And to perform a set, we know that all we have to do is an OR between the 256 bits and the mask, because we know with any two values, any of the two values in OR equal to 1 means that the result is 1. Vice versa, if you want to unset, it's similar, but in this case, we're doing a inversion of the mask. So we're setting to 0, that specific point, and 1 to all the others. And performing the AND means that only for that specific position, we're setting it to 0. So just a quick overview on bitmaps there. Another important standard is the ERC 721 enumerable. This one allows the important functionality of knowing which are the tokens and accessing in an efficient way the tokens owned by an address, or in general, all the tokens that have been minted. It introduces two data structures, in general, 4 in total, but 2 specific concepts, an owner's list and a total tokens list. In the owner's list, we're basically tracking an owner to an index, basically, in this tokens index, and it returns the token ID the owner owns for that index. Vice versa, token ID to this UNT 256 returns the index within the owner's list. In this case, instead, we have all tokens, and all tokens index, given a specific token ID, returns the index within the all tokens array in order to retrieve with a O of 1 computational time, basically the token ID you need. Why this extension? Because it allows functionality like this, token of owner by index. So you can basically iterate or get a specific token of an owner if he owns more than one. In fact, it checks if the index is greater than or equal to the balance of. In that case, you're accessing out of the bounds of the array, let's say, of tokens the owner has. Otherwise, it returns simply the own the token for that specific index. So imagine the scenario, you want to retrieve the information of the tokens of an owner. You iterate from the 0 index to the balance of the owner -1. And through this method, you're able to receive all the token IDs owned from the owner. Last but not least, ERC-721 votes, similar to the ERC-20 votes extension. In this case, you have your NFT as the voting power. So it's 1 unit of vote represented by the NFT itself you own. So you have, if you have more than one, you have more than one voting unit of power. And it's similar to the ERC-20 contract. But in this case, what's happening is that when transferring one NFT to another, you're also checkpointing the fact that 1 unit of voting power has been transferred from one account to another. And why this extension? Because obviously NFT connections in time created the necessity for their holders to be able to participate in a governance system. So instead of a token as the voting power, the NFT holders became basically eligible for voting in those kind of DAOs. Okay, and let's proceed to the next standard, and that's the ERC 1155. So ERC 1155, again, with the example in the mall, in the shoppers example, can be seen as bundles, in this case, like an exclusive sneaker bundle. So imagine I have this bundle where I'm offered a special edition 1-of-1 sneaker pair, and together with that sneaker pair, I get some socks. Why this example? Because ERC 1155 token standard allows for the multi-token standard creation. So you can combine both fungible and non-fungible tokens within the same standard. What does this allow? This allows, within its implementation, efficient batch transfers. It performs the updates to the storage state variables in an atomic way, so within the same transaction. And how it's implemented also allows efficient storage rather than combining your own custom implementation of allowing both. That might not be the most performant way. Quick look at how this works. Let's go to our source code and then my mall items. Here we are extending again the implementation by OpenZeppelin, and the key difference here with the other standards is that you don't have token IDs, but you have token types. So here we're defining 2 types, socks type and the sneaker type, and upon deployment we are minting 10 socks to the deployer and 1 limited edition sneaker. Also, key difference with the URI in this case is that you're not returning a pointer to the metadata to that specific token ID, but you're actually returning a pointer to this specific token type. And what usually happens is that this is a specific format, so it's always the same, and then it depends on the Web3, let's say, interface, the front end that actually reads this and needs to parse or substitute where the squiggly part is defined, basically to know the specific metadata for that token type. And quick look also here is that the key difference is that for balances now you have a balance regarding the token type and not simply just an account and the balance of tokens they have. How this is implemented in an efficient way all relies again in the core internal update function, and this handles both single transfers and batch transfers of multiple token types. You can see here you can transfer from an origin to a destination, and you can specify more than 1 token type. In this case, they're called IDs, but imagine them as token types. Otherwise, you get confused with the token IDs of the NFT standard. And values, so what is the amount of transfer for each token type? Here we simply check that the 2 arrays are of the same length. Then we get the operator, whether it's the owner or the approved operator, and then we perform, by iterating through the different IDs, a transfer of the value we specified. So we simply check if the balance is there. Otherwise, we do an unchecked decrement of the value, similar to what we've seen with the ERC-20. And if the to address is different from the 0 address, so we're not burning again. So here we're checking if it's not a mint and it's not a burn, we're incrementing that value for the destination. As we said here, it supports both single and batch transfers, so it checks the length, and if it's a single token type we're transferring, it emits a transfer single event, otherwise a transfer batch. Quick extension here also is the supply. So this one is for those use cases where you want to quickly track what is the supply of the token types within your ERC 1155 standard. In our case, if we extended this, we could have simply seen that the sneaker, because it's a 1-of-1 limited edition, has a one supply, is a supply of 1. And we can then basically imply that that's an NFT, that's a non-fungible token, but also a unique non-fungible token. Whilst the socks, upon deployment, have a total supply of 10, so we can then see those as fungible tokens within the same contract. Okay, great. Last thing, there are solutions that exist like playgrounds, so that you don't have to manually think of this all by yourself. You can simply open, for example, OpenZeppelin's like a wizard playground, and here, based on your type of token, you can define what functionalities it has and what extensions it has. For example, you can define an ERC20 that has the votes functionality like we saw, but instead of block number based, it's timestamp based. So each checkpoint is based on a timestamp. In that case, would be the block timestamp instead of the block number. And you can even make it, I don't know, burnable. So you can easily burn those tokens or by the owner or the approved, etc. And yeah, we have 20 minutes. So I wanted to also look at a bonus part that's not part of the EIP 712, ERC token standards, which is the EIP 712. But if we're not able to do this in time, I'd want to look at this. Maybe I invite you guys to look at this in your spare time after this lesson, or when you can, because this is a very important standard that solved a lot of issues. Also in merit to the security standards that in the past, unfortunately, we do not have. Like, how many times have you interacted with a contract that asks you to sign a message, and that message is literally a hex string and you do not know what you're signing? This standard exactly solves this by also even solving ambiguity problems, whereby you're signing maybe a message for a specific contract of a specific chain, but then if you sign something that does not check for this so-called domain, then that signature could be valid for another contract, maybe in another chain, therefore resulting maybe in exploits. So this standard, what it does, it solves these two issues. So first of all, it allows wallets to showcase what the user is signing in a human-readable format, and also solves the ambiguity whereby you could be signing something that's not related to the specific contract in question. How it works, again, is that you have a domain. This domain is created by a name, a version, a chain ID. So the ID of the chain you are deploying and utilizing this contract, and a verifying contract, which is usually the contract itself, the address of the contract itself. Say, for example, in this use case, I have a message to sign, and what this message does, it simply updates a mapping saying that from this address, I have written this message. How this works is through the verify and store. So I can verify and store this message by checking if the from address is actually the signer of this method. This means that the caller doesn't have to be the signer, but he can have the signature from the signer. Imagine like a backend that received the signature from the front end, whereby the user connected with his wallet, he signed. He gave his signature, like he signed for this operation to happen, and then a backend, another account maybe calls this function and performs the operation for him. How this works in technical terms is that we are getting the struct hash. With this struct hash, through this implementation here, we are able to get a digest. Through the digest and the ECDSA curves, we're able to recover who the actual signer is. Now, this is more, let's say, complex cryptography stuff. I highly invite you to look into this because it's even correlated with the generation of private keys. It's very useful, let's say, in the blockchain industry. But in summary, once we have the signer, we simply check if the signer is the from address we specified. We're not checking, in fact, that the caller of the function is the same. And if this signature is valid, then we can perform the storage update. Quick example here is, this one. So as we can see here, what message we are signing is hello EIP 712, and it's from this address here. So first of all, we're getting the domain. As we can see, the domain here is the one we saw in the EIP 712 struct hash, and we have a name, a version, and these are in fact identical. We can see here are identical upon construction of the contract, because the name and version are passed to the EIP 712 abstract contract. Then we can see the chain ID is the chain where this contract is deployed. In this case, because we're using the hard hat network, it will be the chain ID of hard hat. And the verifying contract address is the address of the contract that was deployed. This means that if any of these change, even though the message is the same, the actual signature will not be valid, thus preventing those cross-chain attacks or cross-smart contract attacks we were talking about. How does the signature work? We're using the sign type data. This is an operation that takes the domain, the types, and associates these types basically to the values we specified in the message. It obtains the signature. If I'm not mistaken, it's a KEKAC signature. Not exactly sure what algorithm was used. But once we obtain the signature, what we can do is then verify and store. So we are calling the verify and store. We're passing the from content and signature. And now as we saw, the signature is being verified and the message is being saved on the storage. So let's quickly test this out, because I isolated the test here, and we can see the message verification storage was successful. But let's see an example instead if the signature is rejected. For example, here. Say I have this user, and so the user is this guy. And what is happening is I'm actually signing the message with a different user. So I'm using the user 2 instead of the user 1, which we saw the check of the signer being the same as the from address. And because it's different, then it reverts. In fact, the invalid signature should revert because the sign does not match the from address. Right, let's run this again. And you can see it's passing. Okay, and then this was a quick overview on EIP 712. Last but not least, an introduction on oracles. So again, quick little story here. Oracles. So imagine like blockchains as isolated environments, no? But in general, like imagine your blockchain, or in general your smart contract, like an isolated island. Within your island, you have the inhabitants. For some reason, they want to know what the result of their favorite sports game was. I don't know why, but yeah. Or what the exchange rate of some gold they just found could be in relation to their coconuts, because they find coconuts more attractive. This is basically what ChatGPT envisioned for this example. I don't know how realistic this can be, but I give this example because you can imagine blockchain environments, smart contracts, as these isolated islands that might need to know information from the external world, need to know external data, because maybe their functionality is strictly tied to this information, this data. In fact, some key use cases about the usage of oracles to fetch this data and therefore bridge the real world data with on-chain data is, for example, decentralized finance. We have oracles that fetch in a more let's say reliable way the price of specific tokens or token pairs, the exchange rate of specific tokens. For example, lending protocols that have these lending and borrowing solutions, and therefore some liquidation thresholds. If you rely on a single point of data fetching, say, in fact, a AMM, let's say, that offers some kind of Oracle solution, but that AMM maybe is exploited with quick liquidity adding or draining, you could trigger these collateral liquidations, thus resulting in a poor performant liquidity protocol. Therefore, using an oracle that aggregates and utilizes different sources of truth and utilize that oracle to know what the actual price is of a token is a lot more reliable than the example I said. Another example could be like supply chain management. You have a contract that depends on what the stage of a specific product is in its supply chain process. that case, you can use oracles to trigger updates on the smart contract. I know one of these, for example, is Origin Trail, and in VeChain we have Toolchain. I'm not sure we have an oracle for this, but it could be a possible product. Another use case could be prediction markets, like we've seen recently with the elections. One killer app that resonated a lot was the Poly Market app, or in general prediction markets on chain. And what they use is oracles to be able to trigger the eventual binary outcome of a bet, let's say. For example, who's the next election winner? And through oracles, then this is possible. And last but not least, a typical example of oracles are random number generators. Because blockchains are deterministic environments, in fact, I wanted to quickly go a bit more in detail in this. If you do utilize purely the block information, say block hashes, etc., you could be subject to predictions of what a possible random number is if you use a pseudo-random solution, like completely relying on deterministic values like blockchain. In fact, this is a key problem, let's say, in those protocols where you don't have a VRF, a verifiable random number function, out of the box. So you need to rely on oracles to be able to obtain a verifiable random number. In fact, VRFs are exactly this, verifiable random functions that then random number generators that though offer a proof, a cryptographic proof that your random generation is actually valid and tamper-proof, basically. One solution to this is Chainlink. Chainlink is a famous oracle in the Ethereum ecosystem. I'm not sure they extended outside of EVM, but what they offer is various solutions, oracle services, such as VRFs, and even price, for price markets, like we said, for liquidity protocols, they offer what the actual exchange rates are in a more reliable way. The Chainlink VRF in particular works by combining, yes, the deterministic values we talked about, but also secret keys managed by the nodes of the peer-to-peer system of the Chainlink protocol. How this works is through a series of steps. Say you have a smart contract that needs a random number. Now the protocol has evolved. It's returning random words that you can then utilize for a random number. But to simplify, once requested, what happens is that Chainlink uses these deterministic values of the blockchain plus its own secret key by the specific node to then obtain the verifiable random number, together obviously with the proof, in order that the smart contract can verify that random is actually tamper-proof and randomly generated. To see more in detail how this works, I wanted to quickly go through one example on how the process works with Chainlink. Chainlink offers two solutions. It's subscription-based and direct funding. In this case, with direct funding, what happens is you utilize the Chainlink token or the native currency of the blockchain to request random words in this case. What happens is that you transfer this link token or the native currency, depending on what solution you choose, to an intermediary, the VRF wrapper. This VRF wrapper basically acts as a coordinator between, an intermediary between the coordinator and your smart contract. And the coordinator is basically this centerpiece that is the bridge between your blockchain and the Chainlink nodes. So with the Chainlink nodes, you then obtain the random function. The proof is also returned to the coordinator, then sent to the wrapper, that then calls the callback function that is inside your contract. In this case, it's a so-called fulfill random words. In fact, if you want to also look into detail on the implementation, all you have to go is in the Chainlink docs, get a random number through direct funding, and you can see exactly how to implement this. Unfortunately, I think with VeChain, this is not yet compatible because, yes, we can deploy the VRF wrapper and coordinator on VeChain because they are Solidity contracts. But I believe we need to allow compatibility with Chainlink to be able to update and interact with those deployed contracts. I might be mistaken, but I think it's not yet compatible with VeChain. It could be a possible extension, a partnership that brings maybe some good marketing. Yeah, and that's basically it, guys. So 8 minutes a bit prior, so hopefully, like here, you have also all the resources if you want to look into detail. And yeah, that's all.